Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Today we're going to solve a real-world optimization challenge for a betting company using Google App Engine. This is a classic scenario that many high-traffic applications face. The betting industry is unique because it experiences massive traffic spikes during major sporting events. Think about the Super Bowl, World Cup, or the Kentucky Derby. Traffic can increase 10x or even 100x within minutes. This makes read performance absolutely critical. Our application is already deployed on App Engine, which handles scaling beautifully. But now we're facing a different challenge: read latency. When thousands of users are checking odds, placing bets, and viewing results simultaneously, every millisecond counts. As the network engineer, you need to understand not just the technical solution, but why each option would or wouldn't work in this specific context. Understanding the current architecture. Let's dive into what we currently have. A two-tier application typically consists of a presentation, application tier, and a data tier. In our case, that's App Engine for the application logic and likely Cloud SQL or Firestore for the database. The problem statement tells us the application is read-heavy. In betting applications, this makes perfect sense. For every bet placed, write operation. There might be hundreds or thousands of users checking odds, viewing statistics, or refreshing results, read operations. Notice how the current architecture shows direct communication between App Engine and the database. Every read request hits the database directly. During peak times, this creates a bottleneck. Even if App Engine scales to handle more requests, they're all querying the same database, which has physical limitations. The latency we're experiencing comes from several factors: network round trips, database query processing time, and potential connection pooling limits. We need to reduce this latency without completely rebuilding the application. Analyzing the options. Now let's examine each proposed solution carefully. This is where understanding Google Cloud Services becomes crucial. Each option suggests adding a different service between the application and database layers. But here's the key insight: not all these services are designed to reduce read latency. Some would actually make it worse. When evaluating these options, I'm thinking about several factors. What is each service designed for? Does it help with read operations? Will it add or reduce latency? Is it appropriate for a betting application's data patterns? Remember, in a betting application, we're dealing with data that changes frequently, odds updates, but is read much more often than it's written. We need something that can serve these frequent reads without hitting the database every time. Why Cloud Bigtable is wrong. Let's start with Cloud Bigtable. At first glance, you might think it's a fast NoSQL database, so it could help with reads. But this is a fundamental misunderstanding of the architecture. Bigtable is designed for different use cases entirely. It's optimized for high-throughput analytics workloads, time series data, and scenarios where you need to process millions of rows. Think IoT sensor data or financial market data streams. Adding Bigtable between App Engine and your existing database would require a complete data migration and redesign. You'd have to sync data between your current database and Bigtable, adding complexity and potential consistency issues. Most importantly, Bigtable doesn't reduce latency for typical web application read patterns. It's not a caching layer, it's an entirely different database system. For a betting application that likely uses structured, relational data, this would be a poor fit. Why cloud storage is wrong. Cloud storage is even more obviously incorrect, but let me explain why someone might consider it and why it's wrong. Cloud storage is an object storage service. Think of it like a massive file system in the cloud. It's perfect for storing images, videos, backups, and static files. But it's absolutely not designed for database operations or reducing query latency. You cannot query cloud storage like a database. You can only retrieve entire objects, files, by their names. Imagine trying to get the current odds for a specific game. You'd have to download an entire file, parse it in your application, and extract the data you need. This would dramatically increase latency, not reduce it. The only scenario where cloud storage helps with App Engine performance is for serving static assets like images or CSS files, which can be cached by CDNs. But for dynamic, frequently changing betting data, it's completely inappropriate. Why BigQuery is wrong. BigQuery is Google's data warehouse service, and this is another common misconception. People hear fast queries and think it could help with application performance. Let me explain why this is wrong for our use case. BigQuery is designed for analytical queries over massive datasets. It's optimized for questions like, what was the total betting volume last month? Or, which games had the highest betting activity? These queries might take seconds to minutes to run, which is fine for analytics but terrible for real-time applications. BigQuery has significant latency for individual queries, often 1 to 2 seconds minimum. For a web application where users expect sub-100 ms response times, this is unacceptable. You'd be adding seconds of latency, not reducing milliseconds. Additionally, BigQuery isn't designed for the high concurrency, small queries that web applications generate. It's built for complex analytical queries run by data analysts, not thousands of concurrent users checking betting odds. Why memorystore is correct. Now we get to the correct answer. Memorystore. This is Google Cloud's managed Redis and memcached service, and it's exactly what we need for reducing read latency. Memorystore acts as an in-memory cache between your application and database. When a user requests betting odds, instead of querying the database, App Engine first checks memorystore. If the data is there, cache hit, it's returned instantly. We're talking sub-millisecond response times. For a betting application, you'd cache frequently accessed data like current odds, game schedules, and team statistics. When odds are updated, you update both the database and the cache. This pattern is called cache aside or lazy loading. The beauty of memorystore is that it requires minimal changes to your application. You add a few lines of code to check the cache before querying the database. There's no data migration, no schema changes, and you can implement it incrementally. Implementing memorystore. Let me show you exactly how you'd implement memorystore in a betting application. The code examples I'm showing are practical patterns you can use immediately. First, you'll need to create a memorystore Redis instance in the same region as your App Engine application. This minimizes network latency. Remember, we're optimizing for speed. The implementation pattern is straightforward. Try to get data from cache first. If it's not there, cache miss. Query the database and store the result in cache for next time. You'll also want to set appropriate TTL, time to live, values based on how often your data changes. For betting odds that change frequently, you might use a 30-second TTL. For game schedules that rarely change, you could cache for hours. This flexibility lets you balance data freshness with performance. Notice in the code how we're also implementing cache invalidation. When odds are updated, we immediately update the cache. This ensures users always see current data while still getting the performance benefits of caching. Performance improvements. The performance improvements from implementing memorystore can be dramatic. Let me share some real-world metrics from similar implementations. Without caching, a typical database query might take 50 to 200 milliseconds, depending on complexity and load. With memorystore, cache hits return in under 1 millisecond. That's a 50 to 200x improvement. Even accounting for cache misses, overall average response time typically improves by 80 to 90%. For a betting application during peak events, this difference is huge. Users placing last-minute bets won't experience timeouts. The odds refresh instantly. The overall user experience is smooth and responsive. Cache hit rates for betting applications are typically very high, often 90% or more. This is because users tend to look at popular games and current events. The long tail of less popular data might not be cached, but that's fine because it's accessed infrequently. The cost efficiency is also impressive. A memory store instance capable of handling millions of requests costs far less than scaling up your database to handle the same load directly. Best practices and conclusion. Let me leave you with some best practices for implementing memorystore in a production betting application. First, always implement cache warming. Before big events, preload the cache with data you know will be popular. This prevents cache stampedes where many requests miss the cache simultaneously. Second, monitor your cache hit rate closely. If it drops below 80%, investigate why. Are you caching the right data? Are your TTLs too short? Use cloud monitoring to track these metrics. Third, implement circuit breakers. If memorystore becomes unavailable, your application should gracefully fall back to direct database queries. Better slow than broken. In conclusion, memorystore is the clear winner for reducing read latency in a betting application on App Engine. It's purpose-built for this exact scenario, requires minimal code changes, and delivers dramatic performance improvements. The other options either don't help with latency or would make it worse. Understanding these architectural decisions is crucial for building high-performance applications in the cloud. Thank you for your attendance. Please subscribe to the channel. Thank you.